Okay, let's try to link together what we already know and work from there. So what I'm going to do is to link the idea of work in the physics sense with kinetic energy. Now we've studied kinetic energy before and we've seen that it depends upon the mass and the speed. I'm using speed instead of velocity at the moment because we are dealing with just a generic idea of moving. Alright, so if we were doing things like the star jumps, which, believe it or not, you will be doing very, very soon as a practice for a lab rider, then because we are moving and we are doing work, there is motion there, and it's over a distance, then we can calculate the amount of work that we're actually going through and doing. Now, I want you to go through these things rather carefully, so let's think about them. Work and energy. We know that kinetic energy can vary. You can have more kinetic energy at certain times and less kinetic energy at other ones. So it can be gained or lost as it's changed. Remember, it's got to be transformed. It can't just be suddenly appear or suddenly disappear. So it's going to be gained or lost, and what's going to happen is there'll be transformation, probably maybe something like friction or whatever, to cause this to happen. Now, if we can work out what the size of the kinetic energy change is, we know that it must have been caused by something. And we are saying that there was work done on an object to either slow down or speed it up. All right? So if we can look at the difference or the change in the kinetic energy, then we can suddenly gain a lot of insight into how much work had to be done. So, if we look at it this way, kinetic energy, or the change in kinetic energy, is equal to the work that we've done in doing so. And so I've got that. Then this allows us to say things like that half mv squared, which is the formula for kinetic energy, is going to equal the work, which is going to also equal force times distance. So we can actually marry those three things together if we would like to. But sometimes we don't need to. Let's say we've got a problem that looks like this. Right, I've got a car, and it's 700 kilos in mass, and I want to know, right, how much work was done by the brakes in stopping it. Now, it tells us it started off with a speed of 25 metres per second. So let's just put that up here and let's see what happens. So we've got mass equals 700 kg. Good, in the right format. We've got a speed, or a v, and it is in 25 metres per second. Again, good, it is there. And what we're going to do is work out the work that was done by the brakes. Right, so let's go through it. So if I'm looking at the distance, if I'm looking at the difference in kinetic energy, I can work out the kinetic energy of when it's moving and the kinetic energy of when it's stopped. And look at the difference. And that will tell me how much work had to be done by the brakes. I hope so. Well, so if it was moving at 25 metres per second, it had times the mass, half times 750 times 25 squared is how much kinetic energy it had. When it stops, it's a half times 750 times 0. 0 means it stopped, no kinetic energy, not moving. So if I do the sums with this, I see that I've got 234,375 minus 0, or 234,375 joules, or some people might put it as 234.4 kilojoules. Now, I would accept either one of those. That would be fine. So we can use the idea that we've just proposed, that changes in kinetic energy must be done because some work has been done on that object, and we can use what we have to calculate how much work was done. I hope that makes sense. Typical question in a physics test.